In this video, I will discuss some NEET PYQs based on the concept of center of mass. For some basics, center of mass can be understood as a balance point of a system of masses. Let's consider a simple system of say two equal masses M and M, which is connected by a massless rod, rigid rod. One can expect the center of mass to be in the middle by symmetry also. Next, let me consider one big mass and small mass connected by a massless rod, rigid rod. In this case, the center of mass will be closer towards the heavier mass. Center of mass can be understood as a balance point of the system of masses. So this system, if I have a support like this, it will not move. Here, this balance point should be closer to the heavier mass. In this one, the forces acting are the weight. Let me assume the earth is here, which is pulling it down. The force G. So the weight of this mass is mg. The force acting on this one is mg. So this force will produce a torque about this point, anti-clockwise direction, and this weight will produce a torque in the clockwise direction about this balance point. So for these two torques to be equal, this distance and this distance should be same, and let it be d. But if the masses are not equal, this distance will be d1, and the distance of this small mass from the balance point will be d2. So this force, which is the weight, will produce anti-clockwise torque, which is mg into d1 about this balance point. Torque is force into the perpendicular distance. So torque about this balance point is mg into d1. And this small mass, the corresponding weight, will produce a clockwise torque of value mg into d2. For this to be the balance point, these two torques should be equal. So this gives d1 equal to m by the big mass into d2. So if the big mass is much heavier compared to the smaller mass, then d1 should be much less compared to d2. That means the balance point should be closer towards the heavier mass. Next, consider two point masses along the x-axis. This is x-axis. The origin of the x-axis is say here, and let the coordinates of this point masses be x1 and x2. That means this distance is x1, and from origin to this m2 is x2. The center of mass will be somewhere between the two masses. Let it be here. So this distance of m1 from the center of mass, let the coordinate of the center of mass be capital X. So this distance is capital X minus x1, because from here to here it is capital X, from here to here it's x1. So this distance will be x minus x1. Similarly, this distance from here to here will be this distance x2 minus this distance x. So it's x2 minus x is this distance, and this is this distance. So the torque about this balance point x due to this weight m1g, which is m1g, and the distance is x minus x1. That should equal to the torque on this due to m2, about this point, which is m2 g into the perpendicular distance x2 minus x. So this will give me x as g will cancel, m1 x1 can be taken to the right side plus m2 x2 by the total mass m1 plus m2. So x is combination of x1 and x2 with the weightages of m1 by m and m2 by m. So whichever mass is heavy, that x contribution will be more. So this can be generalized for more than one point mass. The third mass can be here, m3, m4 can be here. It can be on the negative side also. Anywhere on the x-axis, you can place the masses. So solve up to the nth mass. So for n point masses, the center of mass is given as summation of individual xi's with the weightage of mass by the total mass. Now instead of restricting the masses only along the x-axis, we can have anywhere along the plane of this board. And see, this is the x-axis, and we can have y-axis here. So all these masses, see 1, 2, 3, 4, 5, and nth mass somewhere here. So here the masses are placed in a plane, xy plane, and the center of mass will be here with coordinates x, y. So x is given by the same formula, where x's are the individual xi's of the individual particles, and y of the center of mass is given by the similar formula, y equal to summation of yi's with the weightage of the mass to the total mass. So now instead of restricting the particles to be on a single plane, it can be anywhere in space. For example, the third mass can be here, fourth mass can be here, nth mass can be here. So it can be anywhere in the space. In that case, center of mass can be somewhere here in space with coordinates x, y, and z. X and y are given the same formula, and z by the similar formula as combination of the individual zi's with the weightage of mass ratio. And this should be sum for all the particles. So this is the formula for x, y, and z of center of mass. This is in general for n point masses distributed in space. It's not restricted to a line or a plane. It can be distributed anywhere in space. So these three formulas we can combine and write as the position vector of center of mass, capital R, is related to the individual position vector of the individual masses. Position vector is a vector, and the weightage is the mass divided by the total mass. So this I have to sum for all the particles. Position of the center of mass, capital R, is capital X I cap plus capital Y J cap plus capital Z K cap. Similarly, R1 will be X1 I cap, X2 J, Y1 J cap, and Z1 K cap. So in particle have Xn, Yn, Zn, Xn I cap, Yn J cap, and Zn K cap. So this is for system of point masses. Instead of having point masses, we can also have a distributed mass. So here the mass is distributed. So in that case, you can take a small part of it, small element of it, of mass dm. This will have a coordinate x, y, and z. So this whole thing will have center of mass somewhere here, and that x coordinate is given as, instead of summation, we have the small mass dm and the corresponding x, divided by the total mass. So the summation will become integration. Instead of point mass mi, we have a small mass element dm with the corresponding x-axis coordinate of this element. Similarly, y of the center of mass is given as integral dm y by the total mass. And z coordinate is also integral dm z by total mass. One more interesting thing is, suppose there is a mass distribution like this, center of mass will be somewhere here in the middle. For example, instead of finding center of mass the whole thing, I can divide this mass into say two parts, any arbitrary two parts, it need not be equal. So I'll just take this part 1 and find the center of mass of this part 1, say C1. And let this mass be M1 of this part. This mass is M2 and M1 plus M2 is the original M, the total mass. And the second part will have center of mass somewhere here C2. So once I find that, I'll make this fold M1 as a point mass here and this fold M2 as a point mass here. Then to find the center of mass of the system, I just have to find the center of mass of the 2 point masses. So I can also break it into 3 parts. See, this is the third part of mass M3. This M1 is different. So this will become C1, C3. So here, the first part M1, I'll make it as a point mass here. Second part, just got the mass M2. I'll find the center mass of that and put as a point mass at the location C2. And this M3 is replaced as a point mass at this corresponding center mass C3. So to find the center of this entire mass, I have to find the center mass of these 3 point masses at this location. An example is, suppose I have a strip in the shape of L. So this is a thin strip. To find center of mass of the system, I can divide it into 2 parts, which will be convenient. I'll take this as the first part. So center of mass by symmetry will be somewhere in the middle, C1, and I can find this M1, which is proportional to the area of the strip, which will be known. Similarly, this center of mass, this second part with C2, whose mass will be M2, which is proportional to the area A2, which will be known. So this full strip, the horizontal strip, I can place a point mass here, and this vertical, this portion of the strip, I make it as a point mass M2 here. Then I have to find the center mass of these 2 point masses. So with this understanding, we solve this NEET PYQs. Timestamps are given in the description box. You can watch parts of video if you are running short of time. I'll discuss some 7 questions. This is the first one. 2 objects of mass 10 kg and 20 kg respectively are connected to the 2 ends of a rigid rod of length 10 meter with negligible mass. The distance of center of mass of the system from the 10 kg masses. You can pause and run this question. This is a simple question. 2 objects 10 kg and 20 kg connected by a rigid rod of length 10 meter. So the center of mass will be somewhere closer to the heavier mass. Let it be here. And let this distance be d1 and this distance be d2. So you have to find d1, distance of center of mass from 10 kg mass. So d1 is the one we have to find out. So this is the balance point. 10g into d1 is this torque, should be balanced by this torque, clockwise torque, which is 20g into d2. So d1 equal to d2, and then d1 plus d2, d1 plus d2 equal to 10 meters, this length. So d2 is half of d1, so this will become 1.5 d1 equal to 10. So d1 equal to 20 by 3 meters. 1.5 is 3 by 2, so it becomes 2 by 3. into 10, so 20 by 3. B is the correct option. Next question. 3 identical spheres, each of mass m are placed at corners of a right angle triangle with mutual perpendicular sides equal to 2 meters. Taking the point of intersection of two mutually perpendicular sides as origin, find the position of the center of mass. 3 masses m, m, m. One is at the origin, one is on the y-axis at a distance of 2 meters. The third one is at the distance of 2 meters on the x-axis. So center of mass formula in the vector form, position vector of center of mass is combination of individual position vectors with the weightage of the mass given by the total mass, and you have to sum over all the particles. So straightforward. So let me take this as for first particle. First particle, the mass is m, and the position vector is y-axis 2j cap. Second mass m, it's at the origin, so 0 I cap plus 0 j cap. So basically 0, it will not contribute. And the third mass is on the x-axis at a distance of 2 meters. Position vector of the third particle is 2 I cap. J cap is 0. It's on the x-axis. And the total mass is 3m. M will cancel. So 2 by 3 I cap plus J cap. C is the correct option. Next question. Two particles of mass 5 kg and 10 kg respectively are attached to the 2 ends of rigid rod of length 1 meter with negligible mass. Center mass of the system from 5 kg particle is nearly at a distance of. 4 options are given. This is similar to the first question, almost same, but with different numbers. Two particles, 5 kg, 10 kg, and the rod is connecting them, massless rod of length 1 meter. Center of mass will be closer to the heavier mass, let it be here, and then this distance will be d1, d2 from 10 kg. So since the balance point, the torque should be balanced. So this torque and this torque both should be balanced. So this torque is 5g into d1, and this torque is 10g, the weight, into the distance d2. So that means d1 equal to 2d2. And the length of the rod is d1 plus d2. Length of the rod, which is 1 meter. We have to find center of mass from 5 kg. So that is d1 we have to find out. So eliminate d2. So 1.5 d1 is 1 meter. So that means d1 is 2 by 3 meters. This is 3 by 2. If it goes this side, it becomes 2 by 3. 2 by 3. So 2 by 3 is 0.67, which is 67 centimeters. Meter to centimeter conversion is into 100. 67 is the correct answer. Next question. Two bodies of mass 1 kg and 3 kg have position vectors I cap plus 2 j cap plus k cap and minus 3 I cap minus 2 j cap plus k cap respectively. The center of mass of this system has position vector. Again, straightforward application of the formula. Formula is position to center of mass, capital R, is combination of the individual position vectors with the weightage of the mass ratio. And this should be sum for all the masses. Here are two masses. First mass 1 kg and the position vector is 1, 2, 1. This can be written like this also. And the second mass is 3 kg and the position vector is minus 3, minus 2, 1. Total mass 1 plus 3, 4. So I cap and I cap will combine. Only this will combine. It's minus 9 plus 1 minus 8. 2 minus 6 minus 4. 1 and then 3 plus 4 divided by 4, which is minus 2 minus 1 1. So minus 2 I cap minus j cap plus k cap. Option is the correct answer. Next question. Consider two particle system with particles having mass m1 and m2. If the first particle is pushed towards the center of mass through a distance d, by what distance should the second particle be moved so as to keep the center of mass in the same position? This is an interesting question. You can pause and attempt it. Two masses m1 and m2. Let the center of mass be here. Let me assume m2 is heavy. Now, first particle is pushed towards the center of mass by distance d. So this first particle has come here. This is the new position of the first particle, and this distance which is being pushed is d. Okay, and this second particle, since the balance point has to be maintained, once this has come in, so this torque has reduced. So we'll try to tilt this way. So this particle should also come in to somewhere here by a distance say d2, which you have to find out. Okay, so in the first case, the center of mass is given as m1 with the coordinate initial coordinate be x1 plus m2 x2 by the total mass m1 plus m2. x1 and x2 are the initial coordinates. This is x1, this is x2. In the second case, imagine the origin is here. x1 has increased by x1 plus d. The second case, x1 will increase to x1 plus d. It's moved by distance d. And then m2, x has decreased by a distance d2. So it's x2 minus d, d2 by the total mass. And the center of mass position is not changing, so x is same. So for that to be same, these two should be same. That means the extra term which has come here, the new terms m1d from here, and then minus m2 d2 from here, that should combine to give me 0. Only then this and this will be equal. That means the x will be same. So that means d2 is m1 by m2 into d. Option B. That is the correct answer. So suppose you consider a special case where M1 and M2 are same. So obviously this thing is moved by D, this also should move by D. So if M1 equal to M2, then D2 is same as D. This is the next question. The center of mass of system of particles does not depend on position of the particles, relative distance between the particles, mass of the particles, forces acting on them. Center of mass, you can also think in terms of x, y, and z. Is summation of mi, xi by the total mass. So it depends on the position of the masses, which is xi, even yi, and zi, and the masses also. But there's no way the force acting on the mass is coming. So it depends on the position of the particles, relative distance between them, that will affect this x, y, and z. Mass of the particles might depend on mass also. So this is the correct option. It does not depend on the force acting on the particle. Next question. This is the next question. Two persons of masses 53 kg and 65 kg respectively are at the opposite ends of a board. The length of the board is 3 meters and weighs 100 kg. The 55 kg man walks up to the 65 kg man and sits with him. If the board is in still water and center of mass of the system shifts by, 4 options are given. You can pause and run this question. So first situation, so this is the board. One end there is 55 kg man. There is a heavier man, 65 kg. Okay, and suppose the two people are same, then center mass in the middle. But since this guy is heavy, center mass is slightly towards a heavier person. In the second case, heavier person and the lighter person are the same side. This guy walks and comes to this end of the board. So for the center of mass to be same, the board would have shifted towards the right by some amount. This is the correct picture. Center mass location is same. See the center of mass location, if external force acting on the system, if it is 0, the center of mass will not move. Will be same. So here when the person is walking, there will be a force between this person and this board, which is the internal force. The system is the two persons and the board. So since there is no external force acting on the system, the center of mass will not move. So the location of the center mass will be same. So the board would have moved like this to make the center mass the same location. So in some sense, about this point, this mass and this part of the board will be balanced by this mass of the board. About this point, this torque will be contributed by these two people and this part of the board. And this torque will be contributed by this part of the board. So here, more part of the board will be on the left side compared to this one. But the center of mass will not move because there is no external force acting on the system. For the center of mass to move, there has to be a force, external force acting on the system. Here there is no external force. Only the force between this man and this board, which is the friction force or normal reaction here. But there is an internal force. So 0 is the correct answer.